Welcome, my name is Malon Janssen. Today I would like to present to you something about the topic of my PhD thesis, volatility estimation under one-sided errors with applications to limit order books. In the context of stock trading on a stock exchange, ask prices on the one hand and bid prices on the other hand can be observed. The bid price is the highest price someone is willing to pay for a stock, and the ask price is the lowest price a stockholder is willing to accept in order to sell the stock. In a non-arbitrage market, the ask price is always higher than the bid price. This leads to the so-called bid-ask spread. This feature shows simulated ask prices, the green dots, and bid prices, the red dots. Between these offered and demanded share prices lies the unknown shadow price, the blue line. We can use a continuous Ito process, X, to model the efficient log price of a stock. The goal is to estimate the total quadratic variation of the Ito process. The right side of this equation is commonly called integrated squared volatility. Now, when we observe data, we always have the values of y. In order to model the ask price above the stochastic boundary x, we use the time-discrete regression type model with an error distribution function f. One natural parametric specification is the gamma distribution, which we also took a closer look at. In particular, therefore the chi-squared distribution, the Erlang distribution, and the exponential distribution also meet this condition. In order to estimate the integrated squared volatility of the Ito process, we use statistical data binning. For a local approximation of x, we choose the local minimum of each block. Similar to the chart on slide 2, here we now see the observed ask prices y in the stock market, the red dots. The black line represents the unknown shadow price, which was simulated as an Ito process. The blue, piecewise constant lines form the blockwise minima, MNK, of the observed ask prices, which form an approximation of the unknown shadow price. To measure volatility, we define the function psi. For this purpose, we consider the expected squared deviation of neighboring local minima. Hn to the power of -1 denotes to the number of all blocks. For each block, we have a local minimum. To the estimator of the integrated volatility. This is the moment estimator for psi. The Hn to the power of -1 belongs to the definition of psi. The number of all blocks. The inverse function ensures that we get an estimator for the Ito process parameter sigma squared. After all, the average of all local parameters sigma squared, those of each block, is formed. Now, let's take a look at the rough procedure. First, we want to show that the function psi is also invertible. After all, as we've just seen, this is used in the estimator. Since the Taylor expansion is used here in the main result, along with the inverse rule, we need that psi and its first derivative are bounded away from 0. and that the second derivatives exist. In addition, estimators for the parameters alpha and lambda must be found. The impact of estimating these parameters on the estimate of the integrated squared volatility also needs to be explored. This forms the main result of the paper. The proof that the function psi, as well as its first derivatives, are not close to zero is very technical and lengthy. Therefore, I do not want to go into it further in this talk. I've listed the main results briefly. Only these constants are important so that we do not reach zero. To estimate the parameters, we first make a parametric approach using the gamma distribution assumption. Here we form the differences of the observations. Since the residual terms of the iter process vanish quickly, we obtain approximate IID gamma differences. This allows us to determine moment estimators for the two parameters alpha and beta. Since odd moments are zero because of symmetry, we need the second and the fourth moments. If we want to use only the first two moments, we can use the absolute values of the differences. I've also done this in my work. However, the system of equations can then only be solved numerically. The lower graph illustrates the convergence rate of the estimators. Since the extreme value index is negative, we are in the domain of attraction of the Weibull distribution. Accordingly, estimating the extreme value index using the negative Hill estimator is useful if one does not want to assume an explicit distribution. To do this, we order our sample for each block and then apply the estimator. Since the negative Hill estimator is shift and scale invariant, we can also plot the estimator with the error terms. Here, h to the power of -1 represents the number of our blocks. This is not the same hn as above. Now that we've calculated the negative Hill estimator for each block, we can calculate a global estimator of the extreme value index gamma by averaging over all blocks. The approximation error consists of the error of transition from the observations y to the error terms epsilon within the negative Hill estimator on the previous slide, and the error of averaging. These two errors must now be balanced so that an optimal block number hn to the power of -1 and a suitable n of the estimator can be chosen. Finally, the convergence rate of the integrated volatility can be determined under unknown parameters. In doing so, we complement this expression to estimate the approximation error of the integrated volatility on the one hand and the approximation error of the local volatility on the other hand. This is the local volatility of each block. This term was added. These are the two terms from the previous slide. We obtain the following two weights, so that we also get the weight of -1 divided by 2 plus alpha for the total result. At the moment, my PhD supervisor, Professor Dr. Moritz Jirak, is working on a lower bound for this problem. Finally, I would like to present a few of the empirical results. In this graph, you can see the results for the parametric estimation procedures. Order book data for Apple stock from August 2010 was used. In the final paper, we will use also recent data. The top two graphs show the estimated values of the parameters of the gamma distribution, meaning the error term. The lower two graphs show the estimators for the parameters of the Ito process. On average, we get alpha equal to 0.055, for beta 39, sigma squared 2.8, and for mu roundabout 0.007. With non-parametric estimation, we obtain similar values. Since I'm currently still working on this, I can only present two graphs. However, it is showing that the parametric estimation seems to make sense as well. Thank you very much for your attention and have a nice day.